In the next 10 to 15 minutes, I will show you two methods to solve for the equilibria in mixed strategies, how to find them. And there's a complicated or a little bit more complicated method, and there's a easier method. And I will start with the more complicated method and save the best for last. So why, if we have an easy method, also to discuss a more complicated method? Well, the reason is that the complicated method starts from first principles. So it starts from the optimization problem that the agents are trying to solve. So let's consider the role player. So he wants to maximize his utility, and given that we're in a situation where we allow for mixed strategies, we talk about the expected utility because it depends on the probability with which each of the players chooses a certain action. And for the role player, the expected utility is as follows. So he chooses to play Italy with a certain probability, PR. And in case that he plays Italy, his payoff will be 2 in case of the row or the column player also plays Italy, which happens with probability PC. And he will receive a payoff of 0 if the column player decides to go for Sweden, which happens with probability 1 minus PC. So this is the expected payoff of the row player playing Italy times the probability with which he will play Italy in equilibrium. Then if he doesn't play Italy, he will play Sweden, and in equilibrium that we look for, he will do so with probability 1 minus PR, in which case he will receive a payoff of 0 if the column player decides to play Italy, which happens with probability PC, and a payoff of 1 if the column player decides to play Sweden as well, which happens with probability 1 minus PC. Fortunately, we can simplify this expression because we have zeros. And if you multiply something with 0, nothing is left. So that is what we will do in the next step. And you please recognize then when trying to find the optimal probability to play Italy, so to find the probability PR, this probability needs to be between 0 and 1 because it is a probability. So that's the constraint on the probability. And now we simplify the objective function, so the expected utility. And we can do so as follows. Well, these terms, they drop out. The other terms, they can be simplified. And we are left with an expression PR times, within parentheses, 3PC minus 1 plus 1 minus PC. And the reason for writing it in this particular form is that now we have only one term with the decision variable of the role player, PR, left. And then we have something that is a function of PC only. And what does that give us? Well, we want to maximize this entire expression by choosing a probability PR correct. And you can see that, well, whether we want to choose PR as large as possible or as small as possible very much depends on the term within parentheses. If this term is positive, then it pays off to choose PR as large as possible. Well, okay, we are bound to not setting it higher than 1. So then we will equate it to 1. If, in contrast, this term is negative, then the player will maximize his utility by choosing PR as small as possible, and you cannot go below 0, so he will set it to 0. That is the mechanism. So it depends on the probability with which the column player mixes between Italy and Sweden. If PC is larger than 1/3, then this thing is positive. So the chance that the column player chooses Italy is sufficiently large. Well, then for the row player, it's also optimal to choose Italy. If instead this value is smaller than 1/3, then probability that the column player chooses Italy is rather low. and it's better for the role player not to mix, but to go for Sweden for certain. So PR identical to 0. And then there's the borderline case where the column player chooses Italy with probability 1/3. Well, then this term within parentheses is identical to 0. It vanishes. So the expected utility of the role player is then 1 minus PC, and PC is equal to 1/3. So the expected utility is then 2/3 for any value of PR. So given that the column player mixes and chooses Italy with probability 1/3, then any value of PR is optimal for the role player, because all of these values will give him an utility of 2/3. So Rowe mixes over his 2 pure strategies, and now we can do the same for the column player. So we have the similar problem. The objective function of the column player reads as follows. The column player maximizes this expected utility function subject to a similar constraint on the probability. Again, we can simplify, please check it yourself, and we get this expression over here. So for the column player, so that is the person who rather goes to Sweden than to Italy, but still the column player will decide to go to Italy for sure if the role player has a sufficiently high probability of choosing Italy. When it's lower than 2/3, then it's optimal for the column player to choose Sweden. And then again, we have a borderline probability of 2/3. So when the role player chooses Italy with probability 2/3 and Sweden with probability 1/3, then any choice of PC is optimal for the column player. It doesn't matter because this first term has vanished. And one of the particular values that the column player could choose, because in that situation all probabilities, all PCs give the same expected payoff. So one of the specific values that she could choose is the value 1/3. Well, and then we go back. Given that the column player mixes between Italy and Sweden with probability 1/3 for Italy, then for the role player, any value of PR is optimal. So for example, he could choose a PR equal to 2/3, because if he chooses PR equal to 2/3, then PC is 1/3 is also an optimal choice for the column player. So now we have found the mixed strategy equilibrium. Both players mix. The column player mixes with probability 1/3 choosing Italy, and the role player chooses Italy with probability 2/3. So combining the results, this is what we find. If the role player chooses Italy with probability 0, it's optimal for the column player to choose Italy also with probability 0, and vice versa. If the column player chooses Italy with probability 0, so certainly the column player decides for Sweden, then it's optimal for the role player also to decide for Sweden. So this is the first equilibrium in pure strategies, and it's consistent with this one. If PR is smaller than 2/3, so say 0, then it's optimal for column to play PC 0 as well, and vice versa. If the role player chooses or the column player chooses PC is 0, then for the role player it's optimal to choose PR is 0. That is the first equilibrium in pure strategies. So we already knew it from the start, but it now also follows from our solution method where we allow for mixed strategies. Also the pure strategy equilibria, they roll out automatically. That also holds for the second equilibrium in pure strategies. But now we've allowed for mixed strategies, we find one additional Nash equilibrium. a Nash equilibrium in mixed strategies, where the row player chooses Italy with probability 2/3 and the column player with probability 1/3. And you can verify that both players in this mixed strategy equilibrium obtain a payoff of 2/3. So, for example, for the row player, we can plug in the values. So this is just plugging in the values in this expression over here. PR equal to 2/3, PC equal to 1/3, and solving it, you get a payoff of 2/3. So here we are using expected utility. We choose our probabilities PR and PC such that we maximize our own expected utility. And note that each of the players would prefer either of the pure strategy equilibria. So it's not that the mixed strategy equilibrium gives you a higher payoff as a player than playing the pure strategy equilibrium, because playing any of these two pure strategy equilibria would give one of the players a payoff of 1, the player that ends up not in the country of choice but with the partner of choice, and it would give a payoff of 2 to the person who ends up in the country of choice with the partner of choice. Whereas here, both players would only get a payoff of 2/3. So either player would, or each player would prefer either of the two strategies or equilibria in pure strategies. We can also show it graphically. So this is the best response function that you know from previous coursework. But now we don't have the different actions on the x and the y-axis, but we have the probability on the x-axis and the y-axis. So this is a notation from the book, but this is the probability with which the row player mixes between Italy and Sweden. It runs from 0 to 1. And this is the probability with which the column player mixes between Italy and Sweden. So we observe that 0, 0 is an equilibrium, because if we map the best response function, say, of the row player, so that's the one over here. This is the best response function of the row player. If the column player chooses Italy with probability 0, it's optimal for the row player to choose Italy with probability 0 as well. It remains optimal for the row player to choose PR equal to 0 as long as PC is smaller than 1/3. When PC is exactly equal to 1/3, the row player is indifferent between choosing Italy, choosing Sweden, or anything in between. So we have a horizontal line on the best response function for the row player. And as soon as the probability with which the column player chooses Italy exceeds 1/3, then the best response of the row player is to choose Italy for certain, so with probability 1. So that is the last vertical part of the best response function of the row player. Now you can also draw the best response function of the column player that goes along the same lines. Well, same mechanism, different lines that we obtain. And combining the two best response functions, we easily find all the equilibria by looking at the points where the two best response functions intersect. And they do so at the point 0, 0. So that's one of our equilibria in pure strategies. The second equilibrium in pure strategies is the point where both choose Sweden with probability 1 or Italy with probability 1. And then here we have the third equilibrium in mixed strategies, where the row player chooses Italy with probability 2/3 and the column player with probability 1/3. So finding the Nash equilibria by looking at the points where the best response functions intersect also works with a situation where we look for mixed strategy equilibria. As promised, also an easier solution method. And now you are ready for the easier solution method because, well, you went through the pains of the more difficult one. So we start with the observation that If a mixed strategy is a best response, then each of the pure strategies involved in the mix, so in our example both Italy and Sweden, must itself be a best response. So in particular, each must yield the same expected payoff. So here we have a mixed strategy equilibrium. It involves the two pure strategies, Italy and Sweden. So given that the column player mixes between Italy and Sweden and chooses Italy with probability 1/3, then the row player mixes between Italy and Sweden, and he mixes between the two. This implies that he's indifferent between choosing either Italy or Sweden for sure, between choosing Italy for sure, or any combination of the two. And because he's indifferent, it means that his expected utility of playing Italy for sure, Sweden for sure against a column player who mixes with probability 1/3, it means that each of these two strategies must give him the same payoff. And we're going to utilize that. So Row's expected payoff of playing the pure strategy Italy against the column player who mixes between Italy and Sweden in some proportion is identical to, well, the row player now plays Italy for certain. So that will give him a payoff of 2 if the column player plays Italy as well, which happens with probability PC. And he will receive a payoff of 0 if the column player chooses Sweden, which happens with probability P-1 minus PC. So simplifying, if the row player chooses Italy with certainty, then his expected payoff is equal to 2 times PC. Now, what about the other pure strategy going to Sweden? If the row player plays that against the column player mixing between the two, well, if he decides on Sweden, his payoff will be 0 if the column player chooses Italy, which happens with probability PC, and the payoff will be 1 if the column player chooses Sweden as well, which happens with probability 1 minus PC. So the expected payoff of choosing Sweden against this mixing column player is 1 minus PC. In the mixed strategy equilibrium, the row player is indifferent between playing either of these pure strategies that is involved in the mix. So for the pair of strategies to be a mixed strategy equilibrium, it needs to hold that the expected payoff when playing Italy is the same as the expected payoff of playing Sweden. So we can equate these two and solve for PC. Because note that so far we said, okay, we want to find a mixed strategy equilibrium, and we know that if we have a mixed strategy equilibrium, then the row player mixes between two of his pure strategies, but he must be indifferent between playing either. But we did not yet specify the value of PC. And now we're going to equate these two, because that needs to hold in equilibrium, and we solve for the value of PC. Now that's easy. So PC needs to be equal to 1 minus PC. Solving, we get that PC is equal to 1/3. And this is no surprise because it's exactly the same value that we found when using the more complicated method. And the same, in the same way, we can also find the equilibrium value with which the row player mixes in the mixed strategy equilibrium. So we use the fact that, so if row is mixing on both are pure strategies in the Nash equilibrium, then both must yield the same expected payoff, in which case column must be mixing with weights 1/3, 2/3. And we use the fact that in this equilibrium, rho must be indifferent between the two strategies that are involved in her mix. And in the same way, we can find the equilibrium value for the rho player, and we will arrive at PR is equal to 2/3, just as in the example before. You can check it yourself. So, well, let's check whether this mixed strategy profile 2/3, 1/3 is really a Nash equilibrium. Does it satisfy our definition of a Nash equilibrium? Well, in order to be a Nash equilibrium, none of the players need to have an incentive to deviate given the strategy by the other player. So, and it's easy to see that this holds in this particular case because we have constructed the mixed strategy equilibrium exactly such that given how column mixes, given PC, the rho player is indifferent between either of his two pure strategies involved in the mix. And being indifferent means that they need to lead to the same expected payoff in equilibrium. And the same argument applies to the column player. Okay, so to summarize, in a mixed strategy, a player randomizes only over those actions among which he or she is indifferent. And if you consider one player's indifference condition, then you can use that to pin down, to determine the other player's mixed strategy. So, final note, John Nash proved the existence of a Nash equilibrium in all finite games, meaning games where each player has a finite number of possible actions. And this existence theorem by John Nash doesn't guarantee that all games have an equilibrium in pure strategies. So if you have rock, paper, scissors, that's, for example, a game that doesn't have an equilibrium in pure strategies. So what the existence theorem says is that each finite game has a Nash equilibrium. So if the game doesn't have a Nash equilibrium in pure strategies, then it must have an equilibrium in mixed strategies. And that also holds for rock, paper, scissors. So you can maybe already guess what is the equilibrium in that game in mixed strategies. And well, you can check whether your hunch is right by doing the formal derivation. And that completes the first part of this lecture.